Hello everyone, this is Anu Agrawal here, and now I'm gonna tell you about rank nullity theorem. So the statement for the rank nullity theorem is given as: let T is a mapping from V to W be a linear transformation and V be a finite dimensional vector space, then the dimension of RT plus the dimension of NT is equal to dimension of V. Here V is a vector space, NT is null space, and RT is rank. Or equivalently, you can write it as rho of T plus mu of T is equal to dimension of V. Now let's come to the proof. Let dimension of V is equals to N and dimension of NT is equals to R. Suppose that the set U1, U2 up to UR is a basis of NT. Since the set U1, U2 up to UR is a linearly independent set in V, so we can extend it to form a basis of V. So there exist vectors, the set of vectors UR plus 1, UR plus 2 up to UN, such that the set U1, U2 up to UR plus 1 up to UN is a basis of capital V. So therefore, R of T can be written as the span, that is L, of T of U1, T of U2 up to T of UN, which can also be written as L of 0 up to 0 and T of UR plus 1, T of UR plus 2 up to T of UN. Because T of U1 up to T of UR is equal to 0, thus we get this statement. So which can be written as L of T of UR plus 1, T of UR plus 2 up to T of UN. We now prove that the set T of UR plus 1, T of UR plus 2 up to T of UN is linearly independent. Suppose the set is not linearly independent, then there exist scalars A of R plus 1, A of R plus 2 up to AN, not all 0, such that AR plus 1 into T UR plus 1 plus AR plus 2 into T UR plus 2 up to AN T UN, which is equal to 0, that is T of AR plus 1 UR plus 1 plus AR plus 2 UR plus 2 plus up to AN UN is equal to 0. So by the definition of null space, you can write it as AR plus 1 UR plus 1 plus AR plus 2 UR plus 2 plus so on AN UN belongs to N of T is equals to L of U1 U2 up to UR. Hence there exist scalars AI where I belongs to between 1 and R, such that A of R plus 1 UR plus 1 plus AR plus 2 UR plus 2 plus up to AN UN is equal to A1 U1 plus A2 U2 up to AR UR. That is, you can also write it as A1 U1 plus A2 U2 up to AR UR minus AR plus 1 UR plus 1 minus AR plus 2 UR plus 2 minus up to minus AN UN is equals to 0. But we know that the set U1 U2 up to UR is a basis of V and so linearly independent. Thus by the definition of linearly independence, you can say that AI is equal to 0 for all I where I is between 1 and N. In other words, we have shown that the set T of UR plus 1, T of UR plus 2 up to T of UN is a basis of RT. Hence, you can say that dimension of RT plus dimension of NT is equals to N minus R plus R, which comes out to the dimension of V. That is, rho of t plus mu of t is equal to dimension of V. Hence, we have proved the given theorem. Now, let's take another theorem which is related to the rank nullity theorem. Let T is a mapping from V to V and T is a linear transformation on a dimensional vector space V. Then T is 1, 1, T is onto and T is invertible. So let's come to the proof. We know that T is 1, 1 if and only if and T is equal to 0. That is the null space containing only the 0 vectors. Then T is 1, 1. Now then by the rank nullity theorem, we know that NT is equal to 0 is equivalent to the condition that dimension of RT is equal to dimension of V. Or equivalently we can say that T is onto. So by the definition, T is invertible if T is 1, 1 and onto. But we have shown that T is 1, 1 if and only if T is onto. Thus we have the last equivalent condition. Hence we have proved these three equivalent conditions. So thank you everyone.